Hello class, and welcome to Module 2, Descriptive Statistics. So two caveats I want to do before we jump into the lecture. The first caveat is the majority of this course we care about inferential statistics for a variety of reasons. One thing is those are newer to you. You probably have not encountered inferential statistics throughout middle school, high school, compared to descriptive statistics, which you probably had in some form in elementary school. So those are new. Those are the more difficult statistics. And a lot of times when we are conducting research, we care about inferring from our sample to the population. That's what we're really interested about here in the discipline of psychology. But descriptive statistics are in their own right very important as well. For instance, many important companies have divisions in which they do a lot of reporting about some of the surveys or data that they have. So there are plenty of people whose job it is to report these descriptive statistics, to put these statistics in a graph or show the data in a graph to their executive, to people that are in charge of the company. I was about to say executive vice president, whatever the particular higher up executive that we're talking about, but a lot of reporting goes on if you are in a company and working with data. All right, so descriptive statistics are very important, even though they are relatively easy for us. A lot of people are not moved by inferential statistics. You know, it might be too complicated for them, but if you display a mean for them, if you get a percentage of people that scored above blah, 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 they might be more moved by these descriptive statistics because it's easier for them to wrap their head around. So descriptive statistics, very important when we are trying to convince somebody of taking some action, when the inferential statistic might be over their head. The other caveat that I want to mention here is that these descriptive statistics are things that you've probably encountered in the past, okay? And so the lecture I'm going to give today, you might think, wow, I knew that in 5th grade or something like that, and I apologize for that. I am bringing things up to date, and I'm talking about some more important qualities of the mean, the median, and the mode, but those are probably things that you have encountered before in the past. So what we're going to do in descriptive statistics, we're going to talk about the 4 moments of a data set, which are the central tendency, variability, skewness, and kurtosis. Central tendency. Most of the time in psychology, we care about measures of central tendency. All right, we want to know which condition did better. To tell that, we look at the mean. Right? Is the mean of the experimental group above the mean in the control condition? All right. Which one of these drugs is the best? The way that we typically compare the data is by calculating an average. So many times we care about mean differences. And in fact, I might argue that 90% of the time in the discipline of psychology, what we care about are mean differences among our groups, among our different conditions, at least if we're doing experimental psychology. All right, so mean difference is very important. And mean is an example of a measure of central tendency. All right, trying to come up with one number that describes the center of our data set. Then we're going to move on and talk about variability. Here we care about the spread of the data. Are all the data points close to the mean? Are they far away from the mean? There are some times in psychology where we're really interested in variability. Variability helps answer our research question. And another thing is that variability is going to give us some insight, as we'll learn later on, about the nature of some of the mean differences. Okay, are the mean differences between the experimental and control condition, are they due to chance, or are they due to a real difference? The way that we're going to make that decision about whether or not these differences are due to chance or if they're due to a real meaningful difference in the population means, is going to be based off of the amount of variability there is in our data set. Might not make much sense right now, but it will make a lot of sense later. So we care a lot about variability in psychology. Variability is very important for us. The last two, skewness and kurtosis. We will talk about These are important as well, especially if we're trying to look at whether our data fit the lovely bell-shaped pattern, the normal curve. So skewness and kurtosis are going to tell us if our data is normally distributed. It fits in that beautiful normal bell-shaped curve. All right, so I mentioned the 4 moments of a data set. Okay, a moment, think of that as a quantitative measure, a single number that gives us some indication of the shape of the data set. Okay, if we were to draw the data set, what's the shape of it going to be like? Is it going to be relatively flat and spread out? Is it going to be relatively peaked? Where is the mean going to be? Is it going to be centered over 5? Is it going to be centered over 10? Describing some characteristic of our data set. That's what a moment is. And there's 4 important moments that we can talk about in our data set that are important to psychologists. One is central tendency, and we're trying to come up with the middlemost value. Try to think, if you would, that you have done some survey. All right, maybe how much do UNG students like the food at the chow hall? And you give them a rating 1 to 10. Okay, how much do you like the food at the chow hall? And then you want to summarize it and talk to the president of the university to change the food or something like that. How would you go about telling the president about the data? Would you say, well, there was one person that picked a 1, and there was another person that picked a 1, and go through every single individual and tell her what score you picked? That would not be a very efficient use of your time or her time, right? So you might want to do it in some other way, all right, to get a single number to describe the entirety of the data set, right? On a 10-point Likert scale, if you said the average of how much people like the food is a 2.5, that's going to get to the heart of the issue that people might not like the food in that regard. So we're coming up with one number that's trying to be at the exact center of that data set. There's many ways of finding central tendency, right? We can calculate the mean, the median, or the mode, and we'll talk about these here shortly. Variability, this is the spread. Okay, how much spread is there? Is the case that everybody picked a 2 for our survey of the chow hall? Or was there a greater degree of variability? Some people put a 1, some people put a 10. The scores are all over the map, okay? This is what variability has to do. It's the spread of our data set. How much are these scores? How much is this data spread out? Okay, we could have an identical mean, but have difference in the variability of the data. These last 2 are going to be harder for me to talk about without pictures. So we're going to talk about them briefly here, and then later on in this module, we'll show you some graphs that will give you some indication of what we're talking about here. We have skewness. Skewness, or the skew of the data, refers to the lopsidedness of the data. All right, are there more scores at the lower end of the distribution, or are there more scores at the upper end of the distribution? Okay, the lopsidedness of our data set. And then we have kurtosis. Kurtosis has to do with the flatness and the peakedness, like how peaked the data is. Is the case that the data is very peaked and that everybody is close to the middle, or is the data distribution relatively flat? Okay, and this is something that's separable from variance, and I'll show you some graphs about this a little bit later on, but just think about these 4 moments of the data going forward. Okay, first in this video, we're going to talk about measures of central tendency. All right, central tendency, we're trying to find one number that describes the exact middle of our data set. Okay, the exact middle of our data set, what's happening in the middle. And there's 3 ways of doing this. There is the mean, and the mean we all know, and we all love the mean. This is the arithmetic average. There's many different ways. When you say average, okay, there's a couple of different averages out there, right? There's the geometric average, there's the harmonic average, but most of the time when we say mean, most of the time when we say average, we're referring to the arithmetic average. That's the one you all know, right? The other ones you mess up. You mess with way further in math. Median, this is the middle score. So we arrange all the data points on a number line or in ascending order, and we picked the middlemost one. That is our median. And the mode is the most frequent score. It's the score that appears the most time in our data set. Okay, so we're going to go into the calculations of mean, median, and mode. I'm sure you guys have probably already done that before, but we'll do it again. But before we do that, I want to talk a little bit about notation. And this is going to be new for you guys. It's easy to explain what the mean is, right? You add all the numbers up, and then you divide by the total number of numbers that you have. It's easy to explain that in English. But for some of these formulas that we're going to talk about in the future, I need to come up with a notation, a symbolic way of telling you what it is that we do. And so it's important to come up with that notation early on for things that we know how to calculate before we get to the more complicated stuff later on in this class. So the first thing that I want to talk about is the summation sign. So this is a summation sign right here. It's an uppercase sigma. All right. If you're in Greek life, you might know what sigma is. So it's a Greek character, and it's an uppercase sigma. All right. The summation sign means to add everything up. Everything that is within the summation sign, you want to add those up. All right. There are two ways that you might see this summation sign. There is an informal summation sign and a formal summation sign. So first, let's look at the formal version of this, go through all the parts, what they mean, and then we will go to the one that you probably see more frequently, the informal version of the summation sign. All right, so here we have a summation sign. We have a top part of the summation sign, and we have a bottom part of the summation sign, and then we have what it is that we're adding up. All right, so we've got this top part, we've got this bottom part, and we've got what it is that we're adding up. Okay, now there's a lot of gobbledygook here. There's a lot of letters as opposed to numbers. So what is it that we're doing? X refers to the value that we're going to add up. Okay, X might be the response times, it might be the memory scores, it might be the attention scores, it might be the heights, whatever variable it is that we're interested in here. Okay, we're just going to call that variable X. I here is the index of summation. Let's say that we have a large list of numbers. The first number in our list, we're going to say, has an index summation of 1. The second number, 2. Third number, 3. So this index of summation is just a number that lets us know which number it is that we're looking at. Okay, so let's say that we are calculating an average and our numbers are 5, 6, and 11. 5 is the first number, so the index of summation for that would be 1. Okay, 6 is the second number, so 2. And then the third number is 11, so it has an index of summation of 3. It's just kind of a running tally of which number in our data set it is. Okay, that's what I means here. N is a very important, I should have bolded this, but you know, we'll talk about it plenty of times. N is the total number of observations that we have. So if we've got 3 things in our data set, 3 numbers, N is going to be 3. In general terms, N is the number of observations that we have. It's the number of data points that we have. In psychology, N means something slightly different or something more specific. Typically, N for psychologists is going to refer to the number of subjects in our research study. So perhaps Chuck, another psychologist, and I are talking in the hall, and I'm describing an experiment, and Chuck tells me that I need to increase the N of my study for it to work out. What Chuck is telling me to do is he's telling me to run more subjects. So N for psychologists most of the time is the number of subjects that we have. So think about that. We'll talk a lot about N in the future. But N in general is the number of observations, specifically for psychologists. Most of the time it's the number of subjects that we have. Okay. So let's talk about what's in the bottom of this summation and what's in the top of this summation. The bottom of the summation tells us where we should start adding the numbers up. All right, this is telling us we should start adding the numbers up at the very first number, when the index summation is 1. That is the very first number in our data set. The top number tells us when we should stop adding things up. All right, the top number tells us when we should stop adding the numbers up. If the top part says n, what we're doing is we're adding the very last number, because remember, n is the number of observations that we have. So if we have 6, we are going to keep adding things until we get to 6. All right. X sub I, this refers to the specific value for x when I is 1, when I is 2, when I is 3, when I is 4, every single one in our data set. So what is this expression telling us to do? Okay, it's fairly simple what it's telling us to do. It's just a lot of notation, and I apologize for that, but I better get you used to it now. This is telling us that we add the first number in our data set, okay, to the second number in our data set. I is going to increase, and it's going to keep increasing until it gets to n. N is the total number of items we have in our data set. So we're going to keep adding those items to one another until we get to the very last number. All right, so this is the formal summation sign that you will see frequently. All right, this is what you'll see in textbooks. But because most of the time we want you to start with the first item and we want you to end with the last item, we can drop these off from the summation sign. And I might just write something like this. This is the informal summation sign. That just lets us know that we're adding all of the numbers up. Okay, we're adding all of the values of x together. You're probably more likely to see this version of it because it's just easier to write out. It's easier for me to type out as well. And the boundary conditions when you start and when you stop don't really change that much for us. All right. So I showed you this because that is how PowerPoint can display it. Many times you will see these, the stopping point and the starting point. You'll see that above and below the sigma sign. All right, so here's an example. This is actually how we're going to write out how you calculate the mean. Okay, and we see the summation sign here, and we see the boundary conditions when you need to start the summation and when you end the summation here. You thought calculating the mean was easy, right? It is very, very easy. But again, for something that's easy, I want to talk about the notation of it so that we are all on the same page. All right, so what is the mean? Okay, what is the mean? It's the arithmetic average of a set of n numbers. Okay, n here is the total number of observations that we have. So the way that we would write out the mean is something like this. Okay, the mean, which we can write it as x bar. This is how we were going to denote a sample mean. We could either do x bar or we could just do m. Okay, both of those are fine. We can do x bar, that's the mean of the variable x. Anytime you put a bar above it, it's the mean. Or we could just put m, and m just means mean. Okay, what we do is we add up every instance of x, okay, add them all up, and then we're going to divide it by n. And again, remember, n is the total number of observations that we have. It's the total number of subjects that we have. So how do we denote the mean? As I mentioned before, anything with a bar over it is the mean. Typically, we're referring to a sample mean there. We could write out m. If you see m, we're referring to a mean, specifically a sample mean. And we're referring to a population mean. And remember, population, that's all of the subjects that we're interested in. That's what we're interested in generalizing to with our research experiment. We write out the population mean, which many times we cannot get unless we have a census, remember. We write it out like this, all right? This is a mu, all right? The way that you would actually write this out is M-U, all right? That's how you would probably spell it. But you pronounce it like mu, like a kitten, like a cute little kitten, mu, mu, mu. So it's a lowercase Greek mu. And it looks like a U kind of thing with this extra bit to it. All right, when we have that, this is our notation for a population mean. So we draw this lowercase mu to denote a population mean. So just an example here. Let's say that we have the following attention scores. All right, we have a few different attention trials where somebody is paying attention to two different things, and then we say, what was that over there? And we see how many items they get right. Let's say there's 10 different trials, and here are the number of trials that our subjects got right out of the 10. How would we go about calculating the mean? Well, first thing that we're going to do is we're going to add all of those numbers up. We're going to add 3, 5, 8, 1, and 6 all up. Okay, that would be 8 plus 8, 16, plus 7 would be 23. I think I'm right. I've got the math right here. Boom. There we go. And we're going to divide it by n. There are 5 numbers here. There are 5 subjects that we have, so n is equal to 5. So if we're doing this math, add all these numbers up. 23 divided by 5, so our mean is going to be 4.6. Okay, so we can either do x bar, or we can write an m equals 4.6. Nothing new here, nothing incredibly complicated, nothing you haven't seen before. All right, so just to reiterate things from our very first lecture, the difference between a statistic and a parameter is the difference between if we're trying to summarize something in the sample compared to if we're trying to summarize something in the population. Specifically for a mean, we use an m or x bar to refer to the sample mean, and a mu to refer to the population mean. And of course, we pronounce it as such. Mu, mu, like the kid. All right, what are some interesting characteristics of the mean? When should we use the mean? First of all, the mean is by far the most common measure of central tendency. It's the most common measure. You will see this many, many times. In fact, you'll see means sometimes where you're not supposed to see means. People love taking the means. And the advantage of a mean is it takes every single data point into consideration. Every single data point in our data set contributes to the mean. All right, if we were to calculate the deviations from the mean, okay, essentially we take every single score and we subtract it from the mean, okay. The deviations would all sum up to 0. That's an important property of the mean. The deviations would all sum up to 0. In fact, if we were to calculate the average deviation from the mean would be 0. Okay, that's an important property of the mean. Okay, because the deviations from the mean all sum to 0, this means that if the mean was used as a prediction of the next score in the data set, okay, let's say that we take the average SAT score of everybody at UNG, and the next person that comes to UNG, we use the average SAT score beforehand to predict what that person's SAT score is. It means that we're going to have the best prediction of predicting that person's score on the SAT, okay? Because that person might be higher, they might be lower, but the mean is going to be the best predictor of the next score in our data set. In layman's terms, that's what that means. Okay, the mean is the best predictor of what the next score is going to be. All right, if I want to guess, let's say that for this class, 23 people take test 1, and I have somebody that's out sick and they have to take the test again. If I were to predict what that person's going to make on the test, I should average those other 23, and that average test score does the best job of predicting what that last person is going to make, given the amount of data that I have already. Okay. The mean is by far the most prevalent, popular measure of central tendency, as I mentioned before, and it is very useful when we have a scale variable. And what I mean by scale variable, again, is if we have a ratio or interval scale of measurement. Means make sense if we have an interval or ratio scale of measurement. If we have a nominal scale of measurement, it doesn't make much sense. Okay, suppose we have eye color, blue is 1, brown is 2, green is 3, and we were to add or take the average of all those numbers. For that nominal variable, that doesn't make any sense. That average would be completely useless to us. So for a nominal variable, I can't really do calculate an average. We've got to use a different measure of central tendency. How about for an ordinal measure? Okay, ordinal scale of measure. How about something like a Likert scale? So you take a questionnaire of personality, and all of these 5 questions measure your extroversion. Maybe we can take the average of that, okay? But it turns out that this is somewhat problematic because, again, the intervals for a Likert scale are not consistent. The psychological difference between a 3 and 4 might be different between the psychological distance between a 4 and a 5. So we have to be cautious if we're using a mean because we might obscure the true meaning of the data because we're dealing with an ordinal scale of measurement as opposed to a interval or ratio scale of measurement. All right, moving right along, we have the median. The median is the middlemost value. What we do is we sort all of our data from the lowest score to the highest score, and we pick the value that's right smack dab in the middle. That is the median. We abbreviate the median by MD, so capital M, lowercase d. So sometimes you will see that if someone's calculating the median. You'll see medians occasionally in psychology, but not super frequently. So if we were going to calculate the median for our attention scores here, the first thing that we need to do is put them in either ascending or descending order. It really doesn't matter. So I sorted these from lowest to highest, and we find the middlemost value. Here it is 5, so the median would be 5. Now, it becomes a problem if we have an even number of observations. All right, so if we have an even number of observations, there's no middle point, right? There are 2 points that are smack dab in the middle. So for instance, if we have attention scores here, now we have 6. We arrange these in ascending order, and the 2 middlemost values are 4 and 5. In this case, to calculate the median, you take the average of those 2 middlemost values. So 4 plus 5 is 9, divided by 2 is 4.5. So we would have a median of 4.5 here. So the median has its advantages. One disadvantage of it is it only takes 1 data point or 2 data points into consideration, right? So it doesn't matter what the highest number is or what the bottom number is, it just matters what the middle numbers are. But the median has many advantages too, all right? So let me tell you about a story. So let's suppose that you are living in a neighborhood, and right where you're at, the middle value, the average of the neighborhood, how much money the household makes, okay, is around, let's say, $60,000 a year. $60,000 a year. All right. And that's a good representation of everybody in the neighborhood. But then all of a sudden, Bill Gates moves into the house next door. Now, Bill Gates, let's say he makes about $1,042,000 a year. He makes a whole lot more than that, but let's just say that for the sake of this argument, that's how much money he makes. Now, because he has such an extreme amount of money, that's going to pull the mean closer to that extreme amount. And now the mean is going to be heavily inflated, and the mean isn't going to represent anybody's data. So if we look at this example right here, most people are clustered here around 60,000. But Bill Gates moves into the neighborhood, and all of a sudden that's going to skew the mean. It's going to bring the mean closer to the side where Bill Gates is. But you'll notice that the mean doesn't do a very good job of representing the majority of households in this neighborhood. So this is problematic. Another way of saying this is that the mean is heavily influenced by outliers in our data set. The median is not influenced by outliers in our data set. So if we have outliers in our data set, the mean is going to change drastically. So what do I mean by outlier? An outlier is an extreme score either at the very high end or very low end of our data set, okay, in comparison to everything else in our data. And an outlier is going to strongly impact the mean of our data set. So here are some examples of some outliers. Here we have the number of sexual partners that people have had. So the majority of people are around 0 to 20. But let's say that we've got Todd here, and Todd has been getting busy, and Todd has over 100 different sexual partners. Now, if we were to calculate a mean here, maybe our mean might be something like 32. But 32 sexual partners doesn't correspond to anybody on this side of the graph. It doesn't correspond to Todd. 32 doesn't do a good job of describing our data set. Okay, so outliers are going to heavily impact the mean. Here's another example. If we're looking at correlational studies, all right, and we can kind of plot a linear line between the variable on the x-axis and the variable on the y-axis, maybe we see some points that are outliers. So here we have one outlier, very easily to see, because if we draw a line of best fit, it would fit through all of these lines, but this line is aberrant. Oh, another great example. So when I do a lot of research, let's say that I'm doing research on the Stroop task, and I show people a single word in a single color, and they have to press a key, one of 3 keys, one key for blue, red, or green words. Now, sometimes we tell subjects that they need to go to the bathroom before the experiment, but occasionally they will not listen to me, and they'll say, I've got to run to the bathroom right here, right now. It's an emergency. And I go, okay. So typically their average response time might be something like 500 milliseconds or half a second. But let's say that Bob, or Todd, yeah, let's make fun of the name Todd. That's good. Todd goes to the bathroom on one trial, and most of his reaction times are about 500 milliseconds. But all of a sudden, we have one trial in which there is a reaction time of 100,000 milliseconds. If I were to calculate Todd's average response time for the Stroop task, that one score is going to completely drown out all of the other ones. And this is going to be problematic, right? It's going to be problematic for me calculating average response time because it doesn't have to do with Todd's attention. It has to do with Todd's bladder. And there's other examples of this as well. If you're doing this task and you're doing thousands of trials of the Stroop task, let's say that you sneeze in the middle of one trial. Well, that is going to throw the trial off. That's going to be an outlier for all of the reaction times that you typically have on the Stroop task. And that's going to artificially inflate what your mean is going to be. So outliers strongly impact the mean of your data set. But not only that, outliers also are going to impact variability to a great extent as well. And that's going to be problematic too. But we'll get to that in another lecture. So some statisticians have argued that if we have outliers, the median is a better measure of central tendency. And that is the case. All right. So let's go back here with our Bill Gates example of how much money people in a neighborhood make. The median is not heavily influenced by these outliers. So in that regard, the median might do a better job of representing what the true central value is in our data set. All right, here's another example. We're trying to calculate the average of something. We've got one outlier over here. The mean is going to be pooled in that direction, and the mean isn't going to represent any of the data, any of our data points. All right, so maybe it's the case that we remove this outlier, and then the mean all of a sudden is going to do a better job of representing what the true middle value is. But this is very controversial. Some researchers are going to say, yes, get rid of the outliers in your data set. Those are going to be problematic and they're going to lead you to incorrect conclusions. And other researchers are going to say, no, outliers are real data and there's probably something interesting going on in those outliers, so don't remove them from your data set. So some researchers are going to argue for the elimination of outliers. Others are going to say perhaps there's something psychologically important going on with these outliers so that you should leave them in your data set. It really depends on what okay, let's go back. This is my personal opinion. Okay, I tell you about the controversy and then I'll tell you about what I think. It depends on what it is that we're looking at. If it's the case that Todd's going to the bathroom in the middle of my Stroop task, I'm going to eliminate that outlier. It's going to lead me to come up with an incorrect solution. It's not something interesting psychologically that's happening to Todd. It's something physiologically happening with his bladder. All right. Yeah. If someone sneezes, again, not very interesting to me. So I'm going to get rid of those outliers in that task. Well, if someone doesn't understand the instructions of your experiment and their data is really, really wacky, I'd say get rid of it. As long as you report who you end up eliminating their data, right? We eliminated data from this person because of X, Y, Z. We eliminated these trials because they were outliers. As long as you have some indication, you are honest and open about why you're eliminating outliers, I think you're fine, all right? So that's my 2 cents. But people differ in this. It's a huge topic of debate within the field of psychology. So when should we use the median? If we have an ordinal scale of measurement, the median is one of the best measures of central tendency. As I mentioned before, the mean, using the mean to calculate an average of an ordinal scale of measurement has problems. Does that mean that people stop doing it? No, people always will calculate the means of an ordinal scale of measurement. All right. How about Likert type items? I see means for that all the time. They're somewhat problematic, and you have to be cautious with your interpretations and how you use that data, but you will see quite frequently that people calculate means for ordinal data. But medians are always good with ordinal data. Okay, if we have outliers, okay, outliers that would obscure the mean, would take the mean and throw it off whack, okay, then use the median. The median is a good way of calculating central tendency. Last thing, if we have a problem with skew, the skewness of our data, and more about which soon, okay, our data is skewed in some regard, the median might be a better representation of central tendency than the mean. So if we have a lovely bell-shaped curve, all right, where most of the people are in the middle, some people, but very few, have an extremely high score. Some people, very few, have an extremely low score. The mean, median, and mode are all going to be fairly similar to one another. But if our data is skewed in some regard, all right, then the mean is going to be heavily influenced by the extreme scores in that skewed distribution. So the median might be a better measure of central tendency in that regard. All right. Mode. The mode is the most frequently occurring score in a data set within a distribution of numbers. So we look at all the numbers. What is the mode? So here we have all of our attention scores, which is the value that occurs most frequently, 3 in this regard. So we're going to calculate the mode is equal to 3. And we're going to abbreviate the mode with a big M and a small o. The letter O, not 0, for mode. All right. The good thing about the mode is it's always going to correspond to an actual data point in your data set. Unlike the mean might have nothing to do with any of the data points in your data set. The mode always is going to correspond to real data in your data set. It's easy to calculate the mode if we have a discrete variable, because discrete variables have a finite amount of values that they can take. So you can calculate a mode fairly easily with a discrete variable. But how about a continuous variable? We can always break things down into a smaller and smaller fraction, right? You're not 60 inches tall, you're 60.36 inches tall. The more fine-tuned, if we're looking at a continuous variable, we're not likely to find the same value more than once. So for a continuous variable, you almost never find a mode in this regard. You can only really do it for discrete variables. The mode makes sense if you have a nominal scale of measurement. All right, so think about eye color, or maybe think about gender identity. These are things where there isn't like a value placed on things, so you can't arrange them in terms of highest to lowest. You can't take an average of particular numbers. The only thing that you can do is find most people are X. Most people have blue eyes in the class. Most people are women in the class. All right. The mode is going to be the measure of central tendency that we use if we have a nominal scale of measurement. It's the only measure of central tendency that is available to us. So eye color, again, doesn't make any sense to calculate a mean or a median. Something like sex or gender identity, same thing. All right, so that's the mode. We can look at the relationship between the mean, the median, the mode for a wide variety of different distributions. We're going to talk a little bit more about distributions later on in this class. In fact, the next module we'll talk about frequency distributions. But what I mean here by distribution, we are drawing a graphical representation of the frequency of particular scores. On the x-axis, we have the value of that score. Do you score very high on it? Do you score very low on it? Okay, maybe this is something like attention. The further out you get, the better your attention is. The lower you get, the worse your attention is. That's on the x-axis. On the y-axis, for these distributions, we have frequency. This is how many people score this level of attention. All right, sometimes we see a lovely bell curve, all right, where most people are in the middle. We see the most numbers, the most observations are around this particular value. So let's look a little bit at some of these. Here we have a distribution that has two modes. Here's mode number one, here's mode number two. If we were to calculate the median and the mean, we would see that it's right around here. So the mean and the median are equal to one another here, but we have two different modes. That's how we would describe this distribution. Here we have a skewed distribution. If we were to calculate the mean, it would be right here, the median here, and the mode is going to be the highest point in this frequency distribution. So it's going to be about right there. Okay. Same thing's going on here. In skewed distributions, the mean, the median, the mode are going to be unequal to one another. They're going to be different from one another. And again, notice that the outliers, the extreme scores here, extreme positive scores, here extreme negative scores, are going to pull the mean towards the outliers. All right, that's what I want to show here. Another thing that we can do with the mode is we can describe a data set by talking about how many modes there are. So we might refer to something as a unimodal distribution, a unimodal, uni, like unicycle, one wheel, unicorn, one horn. Unimodal means that there's one mode in the distribution, all right? The mode here is the tallest point, it's the most frequent score. So this would be our mode here. Here we have our lovely bell-shaped normal distribution. Okay. We could have a bimodal distribution. All right, bi, like bicycle, means two. So this is a data set that has two modes. So here's an example here. We have one mode centered around -2 and one mode around 1.5, whatever our dependent measure is here. But I don't want you to take, when we describe distributions like this, a literal interpretation of mode. Okay, it is the single value that has the most frequent number of observations. All right, because in many instances we're concerning ourselves with continuous variables that there's no really way to calculate modes. So in this sense, we might refer to our modes as places in our distribution where there is a peak, where there's a lot of people scoring around this value. So let's say we look at this distribution. Okay, there are a lot of people that are scoring around here. There are a lot of people that are scoring around here. I would describe this distribution, okay, or this data set as being bimodal. Even though this particular value is not as high as this one, I would still call the distribution bimodal because there's two peaks in this distribution. There's two points in time where there is a peak, a highest value. All right, and we could describe a distribution or data set as being multimodal. So when they have three or more modes, here's an example right here. You're very unlikely to see a multimodal distribution. Most of the time you'll see a unimodal distribution. Sometimes you'll see a bimodal distribution. So for instance, when I am grading tests in class, and there's some people that do well, and there's some people that don't do well. All right, there's the people that come to class, and there's the people that don't come to class. Sometimes I'll get a bimodal distribution when I'm grading things. Right, there's people that get it, and it might be centered around like a 90. Okay, most people are clustered around a 90 or maybe an 85 or something like that. And then there are the people that don't get it, and maybe scores are clustered around a 65. Okay, so I might say that my grades in some of my classes might fit a bimodal distribution. All right, here's another graphical representation here of a unimodal, bimodal. Words are difficult today for me for some reason, and a multimodal distribution. Let's look at some actual data. So this is from 538.com. This is Nate Silver's website, a statistician. He does a lot of political statistics. Very cool website, by the way. Here we're looking at the age distribution of American girls named Violet. And we calculate in each year how many young baby girls are named Violet. So look at this black line right here. How do we describe this distribution? All right, there's a ton of Violets in the early 1900s, okay, and then the name kind of dies off and no one names their kid Violet. And then all of a sudden there's a resurgence where lots of parents name their baby girls Violet. All right, so I might describe this distribution as being bimodal, right? There's a mode here in the early 1900s, and there's a mode right here in around 2010. All right, so that's how I would describe this distribution. Even though this value, how many people are named Violet, here it's about 4,000, here it's about 5,000, right? They're not exactly the same. So if we were going to calculate the mode of a data set, we wouldn't necessarily, if we were calculating the mode actually for a data set, this might not come up, but we would describe the distribution as a bimodal distribution, right? Seems people like the name Violet in the early 1900s, and there was a resurgence of it. We would call it a bimodal distribution. I hope that makes sense. We use the term mode to refer to the most frequent value, and we can also use it to describe a particular data set, describe a frequency distribution. So last, when should we use which measure of central tendency? So the default, calculate the mean, okay? The mean is most commonly used when we have no outliers. The mean is great. When we have a ratio or interval scale of measurement, the mean is a great measure of central tendency. The median we're going to use if we have a large number of outliers and we don't want to remove those outliers. We can calculate the median for a ratio, interval, and ordinal scale of measurement. So particularly if we have an ordinal scale of measurement, the median might be the best way of calculating a measure of central tendency. But again, this isn't going to stop people calculating the means for ordinal data. You'll see that all the time, even when it's not the best option. The mode we should use in a few cases. One, if a particular score really dominates the data set, it's important to report the mode. Let's say a distribution has multiple modes. Okay, it's a bimodal distribution, it's a multimodal distribution. In that situation, it's important to note what those modes are. And if our data are nominal, there's no other measure of central tendency as opposed. There's no measure of central tendency except for the mode. So the mode's the best thing that we got, so might as well use it. All right, so those are measures of central tendency. Now again, you guys have had this stuff before. You've probably had it in elementary school or middle school, but I wanted to talk about some properties of these things. I wanted to talk about outliers. I wanted to talk about when you use the mean, the median, the mode. And I wanted to talk about some notation, because we're going to get into that notation a little bit later on. So make sure that you understand what N is, what I is, what the summation sign is. All right? Thank you guys, and I hope you have a wonderful day.